Hello everyone. In this video, we're going to be solving this system right here, creating a bond graph and creating a system of equations for this electrical system right here. So first off, we're just going to dive in. We're going to say, find the common sources of effort and flow. What is effort in an electrical sense? Well, effort is voltage, and flow is current. So let's find our common sources of current first, because that's pretty easy to do. In an electrical system, the common sources of current are just going to be the current loops right here. So you have I1 and I2, the two current loops. So you already know that you're going to have two ones right here. And you also know that you have a common source of voltage. How do you know that you have a common source of voltage? Well, in between you have a capacitor, right? This capacitor right here is actually connected to three different subcomponents, if you can visualize that. This first subcomponent is this one right here, and the second subcomponent is this one right here. And they're all at the same voltage if you take this capacitor in the middle to be one component. If you look at the voltage differential between this point and this point, you notice that they're actually the same. So that's a common source of effort, or you're going to put a 0 right there. And so let me draw out our ones and our zeros so that you can see how we're going to start this bond graph, right? We're going to have a 1 right here. Let me switch pens so it's a little clearer. We're going to have a 1 right here. We're going to have a 0 right here for the common voltage, right? And for the other current loop, we're going to have a 1 again. And then we're going to connect these together. Now, I'm not going to put the arrows just yet because I want to go over the first current loop before we put the arrows directing to the other junctions. These are the junctions. The ones, the zeros are the junctions, right? They're the junctions of common effort and common flow. Next, I'm going to look at this first junction right here, the one on the left-hand side, and I'm going to say, well, there's a source of flow or current into the system, right? This I right here is a source of flow into the system. Well, then I'll just put an arrow right here. That's going to be the source of flow, right? Next, there are components that are dissipating energy from this junction. The first component that's dissipating energy is these resistors right here, right? R1 and R2. So the arrows are pointing out because they're dissipating energy. They're taking energy away from the junction. What else is taking energy away from the junction, from this current source? Is that capacitor right there, and that's at the 0 junction, right? So we're going to point the arrow in the 0 junction, and as you can see, there's two different parts to the 0 junction. There's this other current loop, that other junction, which is common current, and then there's this junction right here, which also has common current and is connected to the capacitor. So theoretically, if I was going to be very verbose about this, I would write it out as such. There's going to be a common current right here that's splitting off from these two junctions, and I'm going to have a capacitor that's coming off that common current junction. However, what I can do, as you can see there's common current right here. What I can do is if I only have one input and one output to a junction, I can actually take out that intermediary junction, and what I'm left with now is when I squash it, I can squash it down to that single capacitor value, right? That single capacitor value right there, which makes it nice and clean for us to do the math later on after we actually make this bond graph, right? Next, what we're going to do is we're going to put an arrow that's dissipating energy away from this 0 junction. As you can see, these arrows that I've placed show that the current is dissipating away from this junction, simply because, this is arbitrary, but it's simply because I have a current source right here. You can actually change the directions of the arrows and your math will turn out correct, simply because you're going to be you're going to have negative numbers, right, for your sources of the directions of which way things are going. And so you can look at that later. It'll make sense once we write the equations. And if you want to, you can try it out for yourself and see if the math works out. But I'm absolutely certain that it does. Next, we're going to look at this junction right here, right? And it has a capacitor, a resistor, and an inductor that are all connected to the common current source, right? Since we have a common current source, I'm going to say that this capacitor right here, this capacitor right here is dissipating energy, so the arrow is going out. The resistor, well, it's storing energy, but it's also dissipating heat, which is energy. Let's look at this resistor, which is actually just purely dissipating energy right here, R3. And we're also going to look at this inductor right here, which is going to be dissipating energy as well. These components are going to be dissipating energy. So this is our bond graph that we came up with for this system. However, we also have to take something else into account, right? And that thing is that we want to show causality. What is causality? Well, causality is a relationship that shows the effort flows through the system. These arrows show flow through a system. We also need effort to be shown through the system, right? And so what we're going to do is we're going to assign a causality to the left-hand component, which is the source, and that's going to go on this side of the equation, simply because this is a source of flow, because current is a source of flow into this junction. So this side can't have that effort marker, because that would make no sense. Then we would have a source of effort that's going into the one junction. One junctions can only have one source of flow that's going in, because they all have common flow, right? If you had multiple flows going into the junction, it would be very confusing, because what flow source would you use for the common flow of that junction? It makes no sense. If you have two different flows, then effectively you don't know which one to select to be your common flow in that junction. So what are you going to do? Well, that's actually simple. You're just going to put the effort indicators on everything else except that common flow into that junction. And as you guessed, it's the opposite for the zero junction, because it's common effort, right? So only one component can have that effort marking, right? And I'm going to put it on this capacitor right here. This capacitor is going to be that one to have that effort marking right there. And so that actually makes sense. But you could say, why didn't you put it here? Well, you'll see why I didn't put it right here when I go through and put the causality on the other elements. And you can actually use this as a rule of thumb. The effort for a mass mostly is going to be on the component side. It's going to flow here, and the effort's going to be on the component side right here, right, for an inductor, right? Any inductive system, you're usually going to have it there, right? And that'll work out. There are exceptions to this rule, but for this class in particular, take that to be the rule of thumb, and you will be great. Next, well, we already have one source of flow into the system. It's going to be this component right here. So everything else has to be an effort. Everything else has to be an effort, and it is. And there's your causality right there. You have one source of flow, and everything else is effort. This really is to simplify your equations. You'll see that if you do it on the effort on the component of the mass, you'll really see the equations start to simplify. It'll make your life super, super, super easy.